chapter 2 is about crystalline materials and basics of crystallography. So what we are going to do is that we're going to look into the structural aspect of materials, and the exact aspect that we'll be looking into would be the atomic level structure, or which is known as the crystal structure. So let's begin with few of the definitions. We will try to define the crystalline materials and units. It says that solid materials may be classified according to the regularity with which atoms or ions are arranged with respect to one another. So it is the solid material in solid materials, atoms are generally arranged in a specific order with respect to one another. A crystalline material is one in which the atoms are situated in a repeating or periodic array over large atomic distances. That is long range order exists. So you call a crystalline materials where atoms are arranged in a way that there is a long range order in the three-dimensional space. So as we have a 2D shape over here, a 2D platform over here, so basically this it's a long range order in which atoms are arranged in x direction, in y direction, and in the z direction, which is out of the screen. So you call a material a crystalline material when there is a repeating or periodic array of the arrangement of atoms over large atomic distances. So atoms are arranged in a periodic manner in all the three directions. It says all metals, many ceramic materials, and there are certain polymers that form crystalline structures under normal solidification conditions. Now, you know that during the liquid phase, atoms are basically, if I have this container with me and I say that there is a molten liquid in this container, atoms would be actually moving in a very random manner. There would not be any periodic arrangement. But as you try to solidify this material, atoms would start arranging themselves in certain order. So this long range order is basically an order that defines the material to be crystalline or non-crystalline. If the order exists for long range, you say that the material is crystalline. If there is no order for a long range, then you say the material is non-crystalline or amorphous. This type of condition, normally atoms gets arranged from liquid to solid phase. So upon normal solidification, that it is taking place very slowly. When you say normal, it means it is taking place slowly. You are not pushing the solidification process, or you're not solidifying the material rapidly. So under normal solidification conditions, all metals, many ceramic materials, and there are certain polymer materials that but for those materials that do not crystalline, this long range order is absent. There may be a condition that, let's say, these three atoms are organized, these three are organized, they may be organized in a specific pattern, but there is no long range atomic order. And when I say atomic order, I am talking about the scale of atomic level, which is in angstrom, 10 to the power minus 10. So at that level, you should have a long range order for crystalline materials. And if the order does not exist, you call the material as non-crystalline or amorphous material. So far, is it clear?
Yes, sir.
All right, great. Now, it says when describing the crystalline structures, that means the structures that have a particular order, atoms are thought of as being solid spheres having a well-defined diameters. So what you do is that instead of you have to associate certain geometric shape with the atoms. So you assume atoms to be in spherical form. in the crystalline structure. You say these spheres are basically arranged in a particular order that exists for a very long range or for a very long distance. This is termed as atomic hard sphere model, in which spheres representing nearest atoms normally touch each other. So normally the nearest neighbor, they are actually touching each other. This may be nearest neighbor may be in the x direction, may not be in the y direction or z direction, but the nearest neighbor is normally touching the neighbor. Sometimes it says lattice is used in the context of crystal structures, in the sense that lattice means a three-dimensional array of points coinciding with the atomic position. So what it's trying to say is that, let's say this is an order that exists, a long range order that exists, let's say in two dimensionals, since we cannot have the third dimension visible to us very easily. So this order is continuous in all the three directions. So instead of having these spheres, what you do is that you take the center of the sphere and you represent the center of the sphere as the center of the atom, and you say that this is the array of lattice points that represents the crystal structure. So you say it's an array of lattice points that is basically representing the crystallinity of your material, or how what is the arrangement. So now you should have understood a crystalline material has an order, a non-crystalline material doesn't have an order, and this order is sometimes referred to as lattice. This for different materials may be different in three dimensions. How? We'll see that later on.
Sir.
Another thing, when we say that it's an order that is repeating itself. G. G.
सर हम लेटिस को भी एक ऑर्डर या शेप ही कह सकते हैं फिर.
Lattice is basically referred to as the specific crystals. Lattice originates from the lattice points. That is the point at which an atom is situated. And you say this material has a different lattice structure as compared to the other one. Why? I'm coming to that. The common thing between materials is that the materials that are crystalline would have an atomic order. All right, this is clear?
Yes, sir.
Is this clear to you? Materials which are crystalline, they would have certain form of atomic order. Clear enough?
Yes, sir.
All right. Now, this order may be different. How? It may be possible that two atoms or three atoms, they are close together in x direction, but they are farther away in y direction. So the order would still be there, but the way that order is repeating itself might be different. Is this clear to you?
Yes, sir.
All right. So how to define the different arrangements? What you do is that you say that atomic order in crystalline solid indicates that small groups of atoms form a repetitive pattern. There is a repetitive pattern. That's why you say it's a long range order. And in defining the crystal structures, it is often convenient that you divide or you subdivide the structure into small repetitive entities. They are called unit cells. It is basically the unit cell. It is a three-dimensional arrangement of atoms. Unit cell is a three-dimensional arrangement of atoms in crystalline materials that is repeating itself in all the three dimensions. Clear? So different materials would have different unit cells. In other words, different materials would have different atomic arrangement. Is this clear to you?
Yes, sir.
And again, emphasizing on the unit cell is the building block of the crystal structure, and it defines the crystal structure by virtue of its geometry and atomic position. This thing would become more clear to you what is meant by the geometry and the atomic position, but it's basically unit cell basically defines an arrangement that is repeating itself in crystalline materials, and different materials would have different unit cells. Clear enough?
Yes, sir.
All right. Moving
सर
on. G.
सर वो समझ आ गया, लेकिन सर आपकी वॉइस में सर डिस्टॉर्शन आ जाती है और फिर सर वो एक फ्लो के साथ सारी चीजें बोली जाती हैं,
एक मिनट सबर
पास
कीजिए।
आ जाता है पहले। ठीक है।
Is it better now?
Yes, sir.
यस सर।
All right, great. All right. So now we'll be looking into three different kind of unit cells. Three different kind of unit cells that metals mostly follow. All right. Specific metals would have specific unit cells, and these three unit cells we'll be looking at one by one. So the metallic crystal structures, as you already know that atomic bonding in metals is non-directional in nature as compared to other materials, ceramics or polymers. The bonding in metallic crystal structure is non-directional in nature. So there is no restriction, or at least there is minimal restriction as to number and position of nearest neighbor atoms. For example, if you look at the example of methane, you knew that you'll have a carbon atom over here, a hydrogen over here, a hydrogen over here, a hydrogen over here, a hydrogen over here. You cannot have more than 4 neighbors for carbon. In metals, there is no such restriction. So metals can have maximum number of nearest neighbor atoms. Let us look at how the three different crystal structures are defined. The three different structures that metals normally follow are face-centered cubic, body-centered cubic, and hexagonal closed pack crystal structure. Now, have you heard of these crystal structures before?
यस सर, नाम सुने हैं।
All right, let's see what these crystal structures are and how can we define the arrangement of atoms in metals. So we'll first look at face-centered cubic crystal structure, which is also known as FCC, face-centered cubic crystal structure. This type of crystal structure is found for many metals and has a unit cell of cubic geometry. So the first thing you should know is that the three-dimensional repeating pattern is of the form of a cube, with atoms located at each of the corners and the center of all the cube face. So this is basically the face-centered cubic structure. Now this is a repeating unit. This is the smallest unit that repeats in metals that follow FCC crystal structure. In this crystal structure, you have each atom situated at every corner of the cube. So there are 8 corners. You'll have an atom situated at every corner, and then you will have an atom that would be situated at the center of every face. So this is one face, the left face. This is the right face, front, back, top, bottom. So you essentially have 8 corner atoms, and there are 6 atoms that are placed at the center of every face. This is the pattern that repeats itself in FCC crystal structure. Now, which atoms or which elements normally follow FCC crystal structure? Aluminum, copper, silver, gold. They are few of the metallic elements that follow FCC crystal structure. So far, is it clear?
Yes, sir.
All right, great.
Yes, sir.
Great. Now we'll try to have a look at this crystal structure and see which atoms are actually touching each other. So these spheres or iron cores touch one another across a phase diagonal. How? This is the arrangement in an FCC crystal structure. The atoms are touching each other along the phase diagonal. Bear with the drawing, please, but this is the way they are joined. All right, so the nearest neighbors, they are joined together across a phase diagonal. If you look along the y-axis or the x-axis, you would see that there is some distance between the atoms, but the atoms along the phase diagonal, they are touching each other. Clear enough?
Yes, sir.
Yes,
Great.
sir.
All right, now in cubic unit cells, you define the length of the cube. This length of the cube is defined by the letter A. This is also known as lattice parameter. Let me write it with some other ink. Lattice parameter is the parameter that defines the geometry of your lattice. So this is lattice parameter A. Now, if I want to define the lattice parameter for aluminum, or if I want to define the lattice parameter for copper, they would be different depending upon the size of aluminum or copper. Is this clear to you? Does this make sense to you?
So kindly repeat.
Lattice parameter, it is the dimension that defines the geometry of your unit cell. If I say that the lattice parameter A is 5 nanometers, yeah, whatever it is, would you be able to define, draw the cube?
Yes, sir.
Yes, sir.
Yes, sir.
All right. So this lattice parameter is the parameter that defines the geometry of the or the geometric dimension of your cube. And if you know the value of A, you can essentially draw the geometry accurately. This value of A would be different for different elements, and it would be dependent upon the radius or the size of that element itself. Clear enough?
Yes, sir.
Yes, sir.
ठीक है, जितना
Yes.
जितना ये छोटा होगा उतना ही आपकी A की वैल्यू जो है वो छोटी हो जाएगी, जितना ये बड़ा होगा उतनी A की वैल्यू बड़ी हो जाएगी. Is this point clear to you?
Yes, sir.
All right, now let us try to develop the relationship between cube length A or lattice parameter A and the atomic radius of the element itself. It must be clear to you that many elements, copper, aluminum, silver, gold, and there are others, they follow the FCC crystal structure or FCC type arrangement. And the size of their lattice or the size of the crystal would be dependent upon the atomic radius of the element itself. And there has to be a relationship between the dimension of the cube A and the atomic radius. Relationship, we know what is this length. What is this length?
A.
A. and this length.
E.
So I can draw a right angle triangle. I will draw a right angle triangle over here. This length is A, this length is A, and this length is essentially 4R, R, 2R, and R. So this length is essentially 4R. Clear enough?
Yes, sir.
Yes, sir.
Yes,
Alright,
sir.
now if I apply the Pythagoras theorem, it would be A square plus A square equals to 16R square. So you would essentially have 2A square equals to 16R square, and A square would be essentially equal to 8R square, and A would be essentially equal to 2 under root 2R. Clear
सर
enough?
ये 4R वाली सर ये जरा रिपीट कर दीजिएगा बात।
बेटा ये आपको नजर
सर आपकी आवाज नहीं आ रही सर सही अभी।
आपकी आवाज कट
सर
रही है।
यस सर, आवाज नहीं आ रही ठीक।
ये कितना डिस्टेंस है? इज इट बेटर नाउ? बेहतर है?
यस सर।
ऑलराइट, तो ये डिस्टेंस कितना है जो मैंने बनाया अभी रेड कलर से? ये डिस्टेंस कितना है यहाँ से यहाँ तक?
2R
सर 1R।
और
सर यस सर आ रहा है।
ये
आर ये सर्कल का सेंटर है, ये का सरकमफ्रेंस है, तो ये डिस्टेंस कितना होगा?
और
ये आर हो गया। ये डिस्टेंस यहाँ तक कितना होगा?
यस सर ये डायमीटर तो सर ये 2R होगा।
और यहाँ पे फिर ये डिस्टेंस कितना होगा?
और
सो व्हाट इज द डिस्टेंस एक्चुअली?
4R।
क्लियर इनफ?
Yes, sir.
All right. So this is the relationship that in FCC unit cell, the lattice parameter A is related to R as 2R under root 2. Clear enough?
Yes, sir.
Yes,
Yes, sir.
no? All right. Now, a total of how many atoms are assigned to an FCC unit cell? When we say FCC unit cell, if you look at this FCC unit cell, this corner atom, a portion of this atom is being shared by this unit cell. Do you agree or not?
Yes, sir.
So this corner atom is shared by how many unit cells?
सर 4 और 2 सर।
One unit cell over here, one
8,
over
sir.
here. Sorry?
8.
सर 4
ये जो है ये अपने नेबरिंग के साथ, इसके साथ शेयर हो रहा है, इसके साथ शेयर हो रहा है, इसके साथ शेयर हो रहा है, और इसी के ऊपर एक लेयर होगी। जी
यस
बिल्कुल।
सर
क्लियर?
8, sir.
यस सर क्लियर।
तो ये एक कॉर्नर एटम जो है क्यूब के अंदर, इट इज बीइंग शेयर्ड बाय 8 यूनिट सेल्स। सो कॉर्नर एटम 8 यूनिट सेल्स के साथ शेयर होता है, तो कॉर्नर एटम का कंट्रीब्यूशन एक यूनिट सेल में 1/8 होगा। क्लियर?
Yes, sir.
ऑलराइट। और ये जो फेस के सेंटर में ये एटम जो है, ये कितने के साथ शेयर हो रहा है?
सर 2 के साथ।
दो के साथ शेयर हो रहा है, क्योंकि एक इसमें होगा और एक इसके साथ जो इधर होगा उसके साथ शेयर हो रहा होगा। तो इसका कंट्रीब्यूशन, जो कॉर्नर एटम है उसका कंट्रीब्यूशन 1/8 है, जो फेस के सेंटर में उसका कंट्रीब्यूशन 1/2 होगा।
1/2. Yes, sir.
Clear? All right. Now there are altogether 8 corner atoms. 8 corner atoms multiplied by their contribution, which is 1/8, would make a total of 1 atom. And there are 6 face-centered atoms, each contributing 1/2, they would make a total of 3 atoms. So altogether in an FCC unit cell, there are 4 atoms that are part of that unit cell. ठीक है?
Yes, sir.
Is this thing clear to you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
All right. Great. Now
Actually, sir,
moving on.
इसको repeat कर दें, please.
बेटा ask me exactly. जब मैं आपको समझा रहा होता हूँ उस वक्त आप you don't reply and then when everything is finished you call up to repeat. जो चीज नहीं समझ आई exactly ask that thing.
सर ये समझ नहीं, ये बता दें 6 मल्टीप्लाई 1/2 कैसे हो, मतलब 6 क्या चीज है, ये समझ नहीं आया।
ये एक आपका फेस सेंटर्ड एटम, ये दूसरा फेस सेंटर्ड एटम, ये तीसरा फेस सेंटर्ड एटम, ये चौथा, ये पांचवा, ये छठा, हर फेस के सेंटर पे एक एटम है।
जी जी, ओके 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 सर।
Yes, sir.
ओके,
There are
Got it.
essentially 6 atoms that are sitting at face center और face center atom की contribution 1/2 है, तो 1/2 multiplied by 6 would give you essentially 3 atoms that are actually the part of that unit cell. Clear enough?
यस सर, क्लियर।
There are 8 atoms which are sitting at the corner in 1/8. So 1/8 multiplied by 8 would essentially be 1 atom that is part of that unit cell. Sum up 3 and 1, this would give you a total of 4 atoms that are associated with an FCC unit cell. Clear enough?
यस सर।
All right.
Yes, sir.
Now, moving on towards the coordination number and atomic packing factor. Coordination number is basically in a unit cell an atom is touching, or the maximum number of atoms in a unit cell an atom is touching. Easier way to understand is you take this atom. We take this atom and we'll see how many atoms are touching this single atom. So if I say this 1, 2, 3, 4, the atoms which are touching this central atom. Is this clear to you?
Yes, sir.
सर आपकी थोड़ी सी आवाज बीच में कट गई थी, तो ये लाइन रिपीट कीजिएगा।
All right. If I take up an atom in this unit cell, which is this atom, I am taking this atom in this unit cell, and I want to see how many atoms are touching this one atom which is being marked as red. I say there is one atom, this atom, this, and this. There are 4 of these corner atoms which are touching this atom. Clear enough? The central atom.
Yes, sir, clear.
All right. Other than this, are there any other atoms which are touching this atom?
सर ये पीछे सेंटर वाले जो हैं,
जी, ये आपको यहां से नजर नहीं आ रहा. This atom is touching the central atom. Clear?
Yes, sir, clear.
This is the 5th atom. Similarly, इसी का रेप्लिका बिल्कुल नीचे होगा, जो आपको नजर नहीं आ रहा बना हुआ, उसका भी हाफ यहाँ पे कहीं पे होगा, जो नीचे से आ रहा होगा. ऐसे ही ये फ्रंट फेस के ऊपर है ना, तो इसी के बिल्कुल नीचे एक और एटम होगा जो इसके साथ टच कर रहा होगा. क्लियर?
Yes, sir, clear है।
वो ये एटम जो है 7th एटम होगा जो कि अंदर जा रहा बोर्ड के, ये भी यहाँ पे टच कर रहा होगा. क्लियर?
Yes, sir.
इसी तरह इसके बिल्कुल ऑपोजिट दूसरी साइड पे एक एटम होगा जो कि इसको बैक साइड से टच कर रहा होगा, बिल्कुल इसी के ऑपोजिट मिरर इमेज होगा इसका. क्लियर है ये चीज?
Yes, ये भी क्लियर है।
तो 8 एटम ये हो गए. अच्छा, अब नाउ लेट्स से कि इसका बाकी का हाफ जो है, ये तो आधा दिख रहा है ना एटम आपको, बाकी आधा तो इधर है. क्लियर?
जी सर।
ये हाफ, ये आपको आपको हाफ एटम सेंटर से कटा हुआ दिख रहा है, बाकी हाफ तो नेक्स्ट यूनिट सेल में, इस वाले यूनिट सेल में जो इसके साथ है।
जी सर बिल्कुल ऐसे ही।
अच्छा, उसमें ये किससे टच कर रहा होगा? जो ऊपर होगा, जिस तरह ये है उसी तरह इसको टच कर रहा होगा।
यस सर।
यस सर।
इसी तरह
Yes,
बॉटम
sir.
से एक होगा, बॉटम से होगा जो इसको टच कर रहा होगा।
यस सर बिल्कुल कर रहा हूँ।
यस सर।
और एक फ्रंट पे होगा यहाँ पे जो कि अंदर की तरफ जा रहा होगा, वो भी इसको टच करेगा। और एक बैक पे होगा जो जब टूवर्ड्स द स्क्रीन आएगा तो टच करेगा इसको। क्लियर?
जी सर क्लियर है।
तो ऑल टुगेदर कितने एटम्स हैं जो एक इस एटम को टच कर रहे हैं? इस एक एटम को टच करने वाले कितने एटम? 16 या 12?
12 सर।
सर
16
12
है।
है।
अच्छा नहीं 12
कॉर्नर एटम जो है ये तो दोनों में एक ही है, ये एक ही एटम है एसेंशियली।
Yes,
जो
sir.
कितने डिफरेंट एटम इन अदर वर्ड्स इस एटम को टच कर रहे हैं?
सर वो 12 कर रहे हैं।
14 है सर।
12
कितने? सॉरी
सर 14।
14 किस तरह?
12 होंगे।
सर
12 होंगे सर।
5 और 5 10 और 4।
5 और 5 10 नहीं, ये देखें, ये 1 2
सर 12 होंगे,
3,
कॉर्नर्स वाले सेम है तो फिर 12 होंगे।
बिल्कुल, ये 1 2 3 4 कॉर्नर के होंगे। और 5 6, एक यहाँ पीछे बैक पे होगा 7, और नीचे होगा 8, ये टच करेंगे। इसी तरह दूसरी तरफ भी टच करेंगे। क्लियर?
Yes, sir.
यस सर।
So there would be exactly 12 atoms that would be touching this single atom in an FCC unit cell. So the coordination number for an FCC unit cell is essentially 12. Clear enough?
सर एक क्वेश्चन था मेरा।
जी पूछिए।
सर आपने जिस एटम के अराउंड बताया कि इसको 12 करेंगे, तो उसके जो ऑपोजिट है सर वो उसको नहीं टच करेगा?
हाँ जी, ये जो आप कह रहे हैं ना, जो यहाँ पे होगा, जो एटम यहाँ पे होगा,
यस सर।
वो इससे टच कर रहा होगा, इसको टच कर रहा होगा, लेकिन दरमियान में गैप होगा।
ठीक है सर, बस ये क्लियर करना था। ओके ठीक है सर।
That would not be touching it. Clear enough?
यस सर क्लियर है।
All right. Now the atomic packing factor, it defines that how much of the space of the unit cell in terms of volume is actually occupied by the atoms themselves. How closely packed the unit cell itself is. Clear enough? Do you understand the meaning of atomic packing factor? It was atoms within a unit cell divided by the total unit cell
सर
volume
आपके
के
आवाज
अंदर।
सर पॉज हो गई थी सर, एकदम से वो रुक गई थी सर।
All right.
यस सर।
Atomic packing factor means that how much of that is occupied by the volume of atoms in a unit cell. Clear? नहीं आ रही आवाज?
यस सर।
सर आपकी आवाज भी कट गई।
Let me change the internet connection. Just give me a minute. All right, can you hear me?
Yes, sir.
यस सर।
Is it better now?
यस सर।
Yes, sir. It's good.
यस सर।
Right. So atomic packing factor means that how much of the volume of the total unit cell is occupied by the atoms itself. कितने atoms इसके अंदर घुसे हुए हैं total जगह atom से कितनी occupy की हुई है. That would tell you how closely packed the unit cell itself is. Clear enough?
Yes, sir.
Yes,
Clear.
sir.
Yes, sir.
All right. So let's first find out the total volume of the atoms. There are four atoms, four whole atoms in a FCC unit cell. We have seen that in the last slide. The volume of a sphere is 4 over 3 pi r cube. So essentially 16 over 3 pi r cube is the volume of the atoms in the unit cell. Clear enough?
Yes, sir.
Yes, sir.
Yes, sir. Clear.
All right. The volume of unit cell itself is a cube. क्यूब का वॉल्यूम ए क्यूब, ए इसकी डायमेंशन है, एंड ए क्यूब वुड गिव यू द वॉल्यूम ऑफ द क्यूब, एंड ए itself is defined as 2 under root 2r. So you can say 2 under root 2r whole cube. This would give you 8 into 2 under root 2r cube. Clear?
Yes, sir.
So if you have to divide the volume of the spheres, it would be 16 pi r cube over 3 into 16 under root 2r cube. R cube would cancel out, 16 would cancel out. You would essentially have pi divided by 3 under root 2. So what is pi divided by 3 under root 2? It is 0.74. That means 74% of the volume is occupied by the atoms within the FCC unit cell. Clear enough?
Yes, sir.
Yes,
Correct.
sir.
So for the FCC structure, the atomic packing factor is 0.74. Calculate how? You have seen how to calculate it. Now moving on to the second sort of crystal structure, which is body-centered cubic crystal structure. It is relatively easier to visualize it. This structure essentially has an atom in the center of the cube, and there are 8 corner atoms. And normally chromium, iron, tungsten, they are the metals that follow body-centered cubic crystal structure, or the arrangement in body-centered cubic crystal structure is followed by chromium, iron, and tungsten. And in this case, you have centers and corner atoms touch one another along the cube diagonal. So essentially, if this is one end of the diagonal, this is the other corner of the cube, the diagonal passes through the central atom, the center of the central atom, and this is the diagonal that is there. Clear? So atoms touch across the cube diagonals. Is this clear to you?
Yes, sir.
All right. Now let's say I want to find out again the relationship between A and R. This length is A, this length is A. So what would be this length? Under root 2A?
2A.
Is it clear? A square plus A square equals C square. Kindly turn off your mic, please. Can you turn off your mic, please? Mohammad Afnan. All right. So what would be the length of the diagonal? The face diagonal. Can you hear me?
Under root 2A.
Sir, under root 2.
Yes, sir.
All right. Now, this length is under root 2A, this is A, and this is the diagonal that passes through the central atom. So the central atom, this is R, this distance is 2R, and then this distance again is r. So you would have essentially a right angle triangle. In this case, this would be 4r. This is under root 2a, and this is a. Clear enough?
Yes,
Yes,
sir.
sir.
Yes, sir, clear है.
ये a हो जाएगा. This is under root 2a. So now if I have to apply the Pythagoras theorem, it would be under root 2a whole square plus a square equals to 16r square. This would become essentially 3a square is equals to 16r square, and you would have a square equals to 16r square upon 3, and a would essentially be equal to 4r over under root 3. Clear enough?
Yes, sir.
Yes,
Clear.
no? All
Yes,
right.
sir.
So, all right. So this is the relationship for BCC unit cell between the lattice parameter A and the atomic radius of the element. And how many whole atoms are assigned to this BCC unit cell? कॉर्नर एटम्स का कंट्रीब्यूशन क्या होता है?
सर इसका 1 होता है.
1/8 कंट्रीब्यूशन होता है.
On the whole, on the
Total
whole.
on the whole, yes, this would be 1 atom.
Yes, sir.
And what about the central atom? इसका कंट्रीब्यूशन क्या है?
1.
Sir, 1.
1, 2.
1 है. 1 multiplied by 1 would give you 1 atom. So altogether there would be how many atoms in a BCC unit cell?
2.
2 atoms.
So there would be 2 atoms that would be contributing towards the BCC unit cell. Clear enough?
Yes, sir.
Now moving on towards the
Yes, sir.
coordination number. Coordination number is easy in a BCC unit cell. This atom is connected, the central atom is connected to how many atoms?
8.
8. So simply enough, the
Yes, sir.
coordination number in a BCC unit cell is 8. Clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Now you have to find out atomic packing
Yes.
factor. You have to find out atomic packing factor. How closely packed atoms are there in a BCC unit cell? Again, volume of atoms in a unit cell divided by the total volume of a unit cell. What do you think? Atomic packing factor for BCC should be higher or lower than FCC? For FCC, it was 0.74. That's
Sir, it is
74.
lower.
So lower.
Sir, for BCC it is lower.
Yes. You could judge that by the coordination number. In FCC, the coordination number was 12. That means there were 12 atoms that were touching a single atom in an FCC unit cell. Since there are less atoms touching in a BCC unit cell, you would expect that less of the space would be occupied by BCC unit cell in a single unit cell. How do you find out again the volume of atoms in a unit cell? Simple, there are 2 atoms multiplied by 4 over 3 pi r cube. This would give you 8 over 3 pi r cube. This is the volume of atoms in the unit cell. Clear?
Yes, sir.
And the total
sir.
volume.
Yes, sir.
जी.
सर ये जो मिडिल वाला एटम है सर ये तो ठीक है 8 बाकी एटम्स को टच करेगा मगर सर ये कोने वाले जो एटम्स हैं ये कितने बाकी एटम्स को टच करेंगे?
आप बताएं ना, इनका कंट्रीब्यूशन आपने निकाला था, क्या कंट्रीब्यूशन है एक कॉर्नर एटम का?
सर वो कंट्रीब्यूशन वाली चीज तो सर मुझे समझ नहीं है मगर मैं जनरली ये कोऑर्डिनेशन नंबर के हिसाब से पूछ रहा
तो
था.
आप अगर आपको समझ नहीं आई तो आप कैसे पता लग सकता है आपको? ये एक कॉर्नर एटम जो है कितने यूनिट सेल्स के साथ जुड़ा हुआ है?
सर ये
आप
तो
देखिए ना,
अभी
इसके
यहाँ से जो नजर आ रहा है वो तो खाली मिडिल वाले के साथ जुड़ा हुआ है.
यार ये एटम जो है ये पूरा एटम है पहली चीज.
नहीं सर क्वार्टर है.
एक एटम इसके इधर होगा, एक यूनिट सेल इधर होगा जिसमें इसका एक पोर्शन आ रहा होगा.
जी सर।
मैं यूनिट सेल ड्रॉ कर दूं अगर, तो ये वाला यूनिट सेल, इसमें ये एटम होगा या नहीं होगा?
यस
ये
सर,
वाला
होगा होगा सर।
जो ये यूनिट सेल है, इसमें ये एटम होगा या नहीं होगा?
जी सर, होगा।
जो
3 और
ये
होंगे सर इसमें।
ये यूनिट सेल है, इसमें होगा या नहीं होगा?
यस सर।
1 2 3 4, इन 4 में है।
जी सर, बिल्कुल।
और इन्हीं चारों के ऊपर एक और लेयर खड़ी कर दो, उसमें
8
होगा या
होगा।
नहीं होगा?
यस सर।
तो 8। Alright,
ठीक है।
moving on, since we have 4 minutes left, I'll quickly cover up the unit cell volume. Unit cell volume A cube would be 4r over under root 3 whole cube. This would be 64r cube over 3 under root 3. And this is the volume of the unit cell. If you have to divide the volume of atoms, which is 8 pi r cube over 3, with the volume of unit cell, which is 64 r cube into 3 under root 3. 3 would cancel out, 8 would cancel out, and we'll have 8. And you would, r cube would cancel out, so you would essentially have under root 3 pi divided by 8. This would give you the atomic packing factor, and this comes out to be 0.68. So if you do the calculation, you'll come to know that the atomic packing factor for BCC comes out to be of the unit cell is being occupied by the atoms. Is it clear to you?